So the very last part of modern physics concerns hadrons. Now, I said that leptons had no internal structure, hadrons do. Hadrons are the particles which contain quarks. Anything that's got a quark in it, either 3 or 2 quarks, well, a quark and an antiquark really, it's called a hadron. So hadron as in the Large Hadron Collider, because it collides things bigger than leptons. Obviously, before the Large Hadron Collider, there was the Hadron Collider, and before that, there was the Lepton Collider, as you went up in energies. So Large Hadron Collider collides large hadrons largely. I'm not sure it does it all. Anyway, it doesn't matter. Right, so a quark is a fundamental particle. It itself has no internal structure, but it forms the internal structure of the hadrons. Protons are a hadron, so are pions. So the 6 quarks in all of matter, there's only 6, up, down, strange and charmed, and top and bottom, which used to be called truth and beauty, until the Europeans, particularly the Germans, objected to truth and beauty. I think they object to truth and beauty generally. Yeah, I'm just going to put it out there. I don't care. Call me what you like. Actually, just call me Neil. That'd be nice. Anyway, there are 6 quarks and also 6 antiquarks. Now, the antiquarks, like the antiparticles in the leptons, have just the opposite charge but the same mass. So an anti-up would be minus 2.3. That would be an anti-up there, you see. Minus 2.3, and an anti-bottom would be plus a third in terms of charge. But their mass would be exactly the same. Now, the composition of hadrons is the first one we're going to look at. Is there, that's a neutron. It's 2 Ds and a U, 2 downs and an up. And if you notice the combination of 2 downs and an up, you get a charge of 0 by adding 2 downs and an up to each other. So there are, in fact, 2 types of hadrons. The famous ones, Big Barry the baryon. Big Barry the baryon has 3 quarks. The chief example is the proton. Now, a proton has up, up, down. And again, if you add it up, it comes to a +1 charge. So a proton is made up of 3 up, up, and up, up, down combination of quarks. Now, the quark idea was come up with a guy called Gell-Mann, who was trying to understand something called the particle zoo, where there were just thousands and thousands of particles being, well, that's a bit exaggeration, it was 260, but there were lots of particles being discovered, and no one could work out what was going on. Turned out a lot of them were shadows, mistakes in the machine, but even then they had to have some explanation. So he decided he was going to try and categorize them as an exercise into having a number of internal structures, and it worked out perfectly. So something he started off as a mental exercise with his students turned out to win him a Nobel Prize. Not bad. Anyway, that was Gell-Mann. Now, Gell-Mann's theory revolved around these internal particles. He also said that if you were antimatter, you'd have the antimatter equivalent. So an antiproton would be anti-up, anti-up, anti-down. See? Quite interesting. Now, these do feel the strong nuclear force. I put that in because remember the leptons don't. Both types of hadrons feel the strong nuclear force. Now, the other type of hadron, which is a little bit less, you might have heard the name but nothing else, is the mesons. Now, mesons, or the measly mesons, as we like to say, well, I like to say, never heard anyone else say it, to be honest, except students who were just going, when I said measly mesons, were going, measly mesons? Quietly, sort of like in a sarcastic voice. Consist basically of a quark and an antiquark, a quark and an antiquark, mixed together into one particle. So there's only 2 of them. They're obviously lighter than the baryons, therefore. However, they must have a quark and an antiquark inside them. Now, the most famous form of this is a pion or a pion. And probably the easiest to remember, though, it's not the one I've written down here, is anti-up and up, which for some reason doesn't destroy itself in annihilation, but sits there quite easily. That is a neutral pion, which we write like that, pi 0. They're mesons, so they're hadrons, so they feel the strong nuclear force. They're not leptons. So here again, it's an internal structure. Baryon, as you can see, 3 quarks, and then 1 anti and 1 not anti, 1 ordinary in a meson. So a proton, there you have a proton, there you have a neutron, we've already discussed them. There you have your antiproton with all your antis. The bar line, the little bar line, see if I can, that bar line there, that means anti. Now there are more exotic particles we see very little except in accelerators. The lambda is a type of particle that has a extra one that we don't get in protons and neutrons called a strange quark. There's also other particles with charmed quarks, and as I already discussed, tops and bottoms, which are heavier again. Now, as on the mesons, let's draw a line through here, they are. Now, the mesons, which are the ones below that line, as you can see, they all have two. There you are. This gives us a positive pion. See, because if you mix the charges of an up and an anti-down, you get +1. Now, if you mix a down and an anti-strange to get a K meson, quite an important one in terms of particle accelerators and particle discovery, you get your K meson. It's a down and an anti-strange. Whereas, as I said just a moment ago, the neutral pion can be an up anti-up. Okay, so this leads to something we call the particle zoo, where all particles we yet know about can be categorized like this. They're either hadrons or leptons. Now, there are particles associated with forces, such as the Higgs boson and things like that, but we don't have to worry about that, luckily, at Leaving Cert. We'll leave that to a higher level for you to discover about. So, as I said, subject to all the forces, you have the hadrons. They feel all four. Baryons are 3, mesons with a quark and an antiquark. Whereas the leptons are fundamental particles themselves, and they don't feel the strong nuclear force, they just feel the other 3. And what do I mean by the other 3? Of course, we've already discussed gravity, great length. We've already discussed the strong nuclear, which is binding energy equals mc squared, holding the nucleus itself together, and electromagnetic positives and negatives you've known since junior cert. But what is the third one? Well, the third one of those 3, the fourth one in all, is the weak nuclear force, and it's associated with beta decay. It was discovered when we looked at the decay of a neutron to a proton with the admission of that, which is, of course, a beta particle, which we, as I said to you, should write like that. A beta particle, even like this, it doesn't matter. You can write it as an electron of beta. They're interchangeable, no trouble. Now, when this was studied in great detail, they found that all of the experiments they did, they could not balance the mass, energy and momentum from the left-hand side with the neutron to the right-hand side. There was some loss. Now, there were lots of theories going around about why there was a loss. Most of them thought it was a problem with the experiment because they didn't think Einstein could possibly be wrong. And then came along Pauli. Pauli said, no, there's too much there and it's too consistent. There must be another particle being produced, and he called it the neutrino because it was neutral and very, very small. Neutrino. It's from the Italian. So he said, well, all right, there is this particle, but you're probably never going to find it. He called it the ghost particle. He said, well, I'd love to find it, but I bet you any money you like I'll never see it. Well, it was like a challenge. That was red rag to a bull to experimental physicists, obviously. They all went looking for the thing. Now, it weakly interacts in extreme. It's neutral, so it doesn't affect any electric or magnetic field, so you can't find it like that. And it's got such a tiny mass that even if it hits something, it does almost no change to it. So it was a very, very difficult particle to discover. Enter Anderson. Experimental physicist, brilliant, called Anderson. This guy Anderson, he came up with the first idea of how to do this. He did it, and it worked. First time. Of course, this was 26 years later, so Pauli had a fairly long wait. But, Nobel Prizes all round, generally very good. Now, it turns out that, and Pauli, of course, didn't know this back in 1930, that the neutrino that was produced is actually an anti-neutrino. It's actually antimatter that's being produced, very interestingly. The little e is because it's associated with an electron production. You also get one that's associated with the tau, you see? So, and another one for the muon. I think that's the muon one. Yeah, there we are. So all of these neutrinos, which are all neutral, have no mass and no charge and are tiny, tiny little things, very difficult to find. And of course we have the neutrino, and we also have antineutrinos. So there's 6 more particles there, neutrino and antineutrino. And it's basically just formed when the electron forms, basically from the beta particle. As the beta particle leaves the neutron and makes it into a proton, this is already a proton, by the way. You can see by the number 4, there were 3 before. This isn't more important. The neutrino leaves, and as you can see, it's anti-electron neutrino. Now, we can write things like this. That's fine. But actually, if you're asked for beta decay, you probably only need that part. The neutrino, if you remember it, great. If you don't worry about it, because it doesn't fit in mathematically at all. I mean, you can't see it's there from the formula. I mean, if a neutron turns into a proton, you need a beta particle to balance the mass numbers here at the bottom. But you don't need a neutrino, so it's easy to forget. But it is there. It's called the ghost particle, postulated by Pauli, found by Anderson 20 years later. Here's another example of it. This is more common. This is carbon-14, which, you know, carbon-14 dating. This is the actual process carbon-14 dates by. Carbon-14 decays to nitrogen-14 with the admission of a beta particle. That's a beta particle, of course. It's the same thing. I write it like that. And our neutrino, which doesn't make an awful lot of difference to the decay, but does, in fact, happen. Okay, so very last section, how do we find all this stuff out? Particle accelerators. This is the first one of any note. This is the one used by Cockcroft and Walton, I mentioned in section 2. This is the little box that Cockcroft and Walton sat in down there. It's just to give you some sort of scale. It's a tiny box. You can just about fit a person into there. So that's the scale of the thing. And it was the very first time we were able to produce a huge electric field, and the electric field would accelerate a particle. So all of this, these things were essentially capacitors. Up here is your hydrogen discharge tube shielded in lead so it doesn't kill everybody. And the particle gets rocketed down here to a target of lithium, which is down there at the bottom. Now, linear accelerators have a problem because particles don't want to travel in straight lines. Due to Fleming's left-hand rule, they want to travel in circles. So very shortly after this, people started to build circular accelerators so that energy wouldn't be used up trying to keep the particle in a straight line. And also these things had a huge advantage of taking up much less space. The first one was really only the size of a very large desk and accelerated a particle more than the one you saw before, which was much, much bigger and more difficult to construct. This one works itself into a circle, which becomes a spiral. And this one is called a cyclotron, accelerating the particle into a circle, using Fleming's left-hand rule. The idea that a particle travelling in a field will always take a circular path because the force is always perpendicular to its direction of motion. So, particle in a field, circular path, force always perpendicular to direction of motion. So, that's more or less everything. We've got this is a modern accelerator. It's circular because it's more compact. High velocities are needed to overcome repulsion because often we're pushing 2 protons together. Protons are both positive, so to overcome the natural Coulomb repulsion, the positive to positive repulsion between the two, we need to put them at very, very high velocities to overcome this electromagnetic repulsion. They're in a vacuum because if they hit an air molecule, they'd stop immediately. So we take everything out so that the particles can't hit anything in the way, and that increases what's called the mean free path. It just means they can go some distance without hitting something. And the more velocity we give them, the more energy we give them, and so we can look first of all at higher energy collisions, which actually take us back further in time towards the beginning of the universe. Yes, and the whole thing is held in place by magnets. Supercooled magnets, huge magnetic forces hold these things in place in what's called a magnetic bottle, because these things are so fast and so hot that if they get anywhere near the sides, they'd lose all their energy. It would all be conducted away. And then we detect what's happening. That's a detector, believe it or not. Supercooled fluid in each of those pipes acts as a detector. Electric signals everywhere all over the pipes, can be picked up. Just to give you an idea of how big this is, that's a guy standing there. This one's called Atlas, not surprisingly. It's enormous. It's also at CERN, of course. As you can see, the building is just... I mean, how did they get the money? Who persuaded them to build this? I don't know. And this is the best question. Now, we haven't done many questions 11, so it's very good. What you're supposed to do is read the section and then answer the questions. What I suggest you do is answer the questions if you can, and if you can't, like, for instance, the very first question says, what is the effect on power of a wind if the wind speed is doubled? Huh? How am I supposed to know? Well, of course, it's written in the section, so you get it from there. But other things like what is electromagnetic induction, well, you can't get that. You have to actually know what that is. Okay, well, you can look that up anyway. So there's a question, there's a force. That's the end of modern physics. That was really brief, wasn't it? That was really short. Wow. Hope the next one will be actually short. It's electron, even shorter.